Good evening to all participants. On behalf of CUP Technological University, I welcome all participants for AICT sponsored Continuous Professional Development Program on Machine Learning Application to Optimization Based Control. This is a 2-week program started from 20th December to 23 December 2022. Basically, this CPDP is consisting of 17 sessions, consisting of some hands-on session, teaching practice session, and there is a discussion on the article related with the machine learning based control. I request head of the department or program coordinator to introduce today's resource person. I request Sonone sir to introduce today's resource person.
Thank you, Professor Girish. Good evening to all the participants. Our respected resource person today, Professor Kishle Mitra. It's my honor to introduce Professor Mitra. Professor Kishle Mitra completed his BTech in Chemical Engineering from NIT Durgapur in 1995. Did his MTech in Chemical Engineering from IIT Kanpur in 97. And in 2009, he received PhD from IIT Bombay. Before joining to academics, Professor Mitra was working GE, TR, DDC, many such organizations, mainly on process control and optimization. Presently, Professor Mitra working as a professor and head of the Department of Chemical Engineering at IIT Hyderabad. His research includes optimal control, bioenergy supply chain design, multi-objective optimization, data science in biology, etc. Professor Mitra has more than 100 international journal and conference papers, book chapters, published in both SCI and Scopus indexing. His research has led to more patents, and those are granted as well. His research papers have been widely cited in technical papers and reference books. He is on editorial board of many journals, Springer Journal, as well as work as a joint secretary for Control Society of India. Professor Mitra has very good collaborations with international academic institutions. His research also funded by Department of Science and Technology, Department of Biotechnology, National Supercomputing Mission, Ministry of Human Resource Development, UKRI, UK government, DRDO, Tata Steel, etc. His collaboration with leading universities like Exeter, UK, Washington University, Seattle, USA, St. Louis, University of Washington, St. Louis, University of Texas, Austin, USA, Deakin University, Australia, and many more. His research group implemented many large-scale machine learning-based optimization and control projects in process plants. He selected among top 2% scientists in the world, 2021 Stanford University list. It's a very prestigious award for him. He received Technical Excellence Award by India Tech Foundation and the Instrumentation and Control Journal in 2001-2. So, friends, we are very fortunate to have such a towering personality with us in the field of process control, optimization, and machine learning. So, I request Professor Mitra, please share his experience and guide the audiences. Thank you. Thank you so much.
So am I audible?
Yes, yes, yes.
Okay. Thank you, Professor Sonavane, for this nice introduction. Thank you, Professor Girish, okay, for coordinating the whole effort. So, all friends, very good afternoon to all of you. So, basically, is my screen visible?
Yes, sir. Yes.
Yes, sir. Yes, sir.
Okay, so as planned, for next 2 hours, our aim is to talk on this particular topic, which is planned for today's evening, that is machine learning for process modeling. Okay, so it's a 2-hour session. I'll be telling you what all I'm going to cover, but then means I would leave it up to the audience. So we'll be talking quite a lot of applications. We'll be talking quite a lot of little bit of theory rather. Okay, so if you feel like that you need a break, say for 5 minutes, say after 1 hour, kindly means feel free to let me know. Okay, so I would like this session to be as interactive as possible. So in that way, kindly means ask questions as well as probably you can let me know. So if such kind of break in the session is needed or not. Okay, so with that, probably we'll start our evening lecture today. So once again, a very good evening to all of you. So welcome to the presentation titled Machine Learning for Process Modeling. So first of all, I thank everyone participating in this FDP for sparing your time and attending this talk. So we are the Global Optimization and Knowledge Unearthing Lab, in short GOKUL, at IIT Hyderabad. We have been working in the field of AI and ML for last many years, and it's my pleasure today to share our working experience with all of you. So it's a little unfortunate that we could not meet in person during today's talk, because in that case, the presentation would have been more interactive. However, feel free to ask questions and make our interaction as live as possible. So this is the brief outline of my presentation. So first I'll be talking about how the tools from machine learning are engulfing and influencing almost every possible field around us. Next, I will try to articulate where does the industrial process engineering stand today, especially in this era of overflowing information. So then gradually, I'll introduce to you several tools of machine learning and their related applications in the areas of industrial process systems engineering that we researched in our lab over the last several years. The conventional fields of engineering, for example, chemical, metallurgical, mechanical, instrumentation, are going through a humongous phase of transition with evolution of some great forces governing these omnipresent disciplines. To name a few, we are now witnessing tremendous progress in theoretical sciences, excellent state-of-the-art experimentation facilities, ever increasing automation of global enterprises, stringent regulatory constraints related to safe and sustainable development, proliferation of competitive business solutions in virtual markets, pressurizing the speed of production, and ubiquitous connectivity across high computing facilities with increased storage capabilities. A common outcome of this transition is generation, processing, and management of enormous amount of heterogeneous data. With contemporary process engineers handling data like never before, the stream of this process engineering is at an important crossroads. On the other hand, the field of computer science and engineering is witnessing rapid growth in terms of development and applicability of novel algorithms for churning voluminous data and converting them into outcomes with scientific rationale that becomes useful for common man. The transfer of knowledge from academics to industry and tangible outcomes from industry to society have never seen such rapid pace in the past. So recent applications of data-based modeling and analysis, more commonly known as data science in the fields of science and technology, have made it as the fourth paradigm of scientific discoveries, the first three being empirical, theoretical, and computational in nature. So data science has been involved in several research activities in the recent times. For example, data science is used in the area of natural language processing to analyze, say, 3 million journals that can lead to novel materials discovery in the field of material science. In another work, deep neural networks are implemented to map Boltzmann distribution for a system of sample equilibrium states for many body systems in much easier and efficient fashion. In another collaborative effort from researchers at Stanford and MIT, machine learning and Bayesian optimization are implemented to develop fast charging protocols of lithium-ion batteries by reducing the time and number of experiments. Activities are not only limited to academia, as we can see in another example. Researchers from the Institute of Minerals and Materials Technology, IMMT, under CSIR, India, in collaboration with DST, Department of Science and Technology, have developed an industrial instrument called Eye on Pellet to monitor pellets of equal size distribution using camera-based image processing in real time. So coming to some very vibrant applications to recent time, you have observed what happened during the initial phase of COVID treatment. Two things we have observed. One is manual testing takes quite a lot of time, while the second thing is it is costly, inefficient, and testing kits were sparsely available. So the question probably asked during that time, can a deep learning based technique do a better and efficient job? So if you observe the two chest X-rays in the slide, one is of a fit patient while the other is for a COVID-19 diagnosed patient. A human eye may not be able to detect the differences in these two X-rays, but given enough such labeled X-rays, a machine learning model like convolutional neural network, CNN, can detect the difference. Even if we think that a human eye can detect, it has to be only by a trained personnel. So however, if a machine or algorithm can do this, a tool can be made out of that. For example, we can attach that with a popularly used device like mobile, and anybody can use it. It can give us a huge benefit. What AI researchers did in this work, in a study reported in 2020, a data set consisting of 3 classes, namely coronavirus, pneumonia, and normal X-ray imagery is created. The data classes were restructured using the fuzzy color technique as a pre-processing step, and the images that were structured with the original image were stacked. Next, the stacked dataset was trained with deep learning models, and efficient features were classified using support vector machines. The overall classification rate obtained with the proposed approach was close to 99%. So apart from this, in general, in the field of life science, medical science, machine learning is creating some mind-boggling research and results that are challenging human capability every moment. Examples go like this. Suppose I am going to show you a picture of retina. Can you detect if this is a male eye or a female eye? Human experts' accuracy is around 50%, whereas AI scores close to 97 to 98% accuracy. In several cases, detection of cancer is missed by radiologists by picked up by CNN looking at the chest X-ray. Compared to the standard practice, MRI images are getting analyzed quicker with better quality with the help of neural networks. Additionally, AI is able to give very quick interpretation without the help of a human expert. In pathology, neural networks can be trained to recognize cancer, which is often debatable among experts, and AI can determine the driver, mutation, and chromosomal abnormalities from the pathological slides. In another instance, smartphone-based ultrasound or echo is observed to deliver excellent images within seconds. The probe is put on in the chest. You can see everything about the heart, for example, heart chambers, blood flow through the chambers. Most impressive revelation is this can be applied to any part of the body except brain, and this can be done without any expert being present. The aim here is not to eliminate experts. The fact is the number of experts are very less. And with this limited resource, how this facility can be proliferated among the huge population of a country like ours. So if a mobile-based tool can do this without taking help of an expert, nothing can be better than that in health diagnostics, right? Developed in academia, hospital industry consortium in US, it is currently in use in Africa to diagnose pneumonia and other diseases. In detection of diabetic retinopathy, Google has already made a product available in the US supermarket that can tell a patient whether she has this disease without taking help of a doctor or an expert. It is performing efficient detection of cancerous lesions or polyps using neural networks during colonoscopy to avoid unnecessarily colon perforation. Near real-time intraoperative brain tumor diagnosis has been successfully performed using simulated Raman histology and deep neural network. You just name them. AI is being tested for probably every avenue where it can benefit a human and the society around us. Apart from healthcare, machine learning is used in forecasting environmental parameters or analyzing the reasons behind the climate change happening around us. Using the current trend, ML can be used for forecasting the future conditions so that looking at future adversaries, a more practical and sustainable practice can be adopted. ML is used to study the melting of Himalayan glaciers and thereby their analyzing their effects on rainfall and other environmental parameters in India. ML is also used to predict extreme weather conditions like Amphan kind of cyclones, etc. CNNs are used to monitor the oceanic degradation due to global warming. In smart farming, deep learning is being used for better monitoring of crops with automated detection of infections and diseases. Other applications include land cover classification, crop type classification, and mapping winter vegetation quality coverage using images from drones. ML is also used for efficient battery management system in electric vehicles. Now coming to some day-to-day uses of ML, machine learning based, these applications probably you know better than me and use in some way or the other. Automatic language translation allows you to speak in your language, whereas the listener can afford to listen to it and interact in her own language. Medical diagnosis, I have already talked about in details. Which stock you are going to invest is going to be recommended by a machine learning based algorithm. This is to be noted that modeling stock market behavior is one of the most challenging tasks in any paradigms of modeling. ML is successfully catching fraud detections, transactions among billions of regular transactions. Take the case of Cortana, Alexa, our virtual personal assistants, who are acting based on our behaviors, and it is backed up by no other than ML. Regular filtering of spams and malwares in our mailing system has become a standard practice without our notice. Cars being driven by ML is no wonder today. Moment you decide to purchase a product in Amazon, you get several recommendations. Thanks to ML. We don't even remember when the habit of driving four-wheelers with traffic prediction switched on has become a part of our life. Cortana, Alexa do not only suggest, but also can recognize your speech. That's even the cooler part that you need not type. Show an image of a flower to Google Lens, it will tell you the name of the flower and history associated with it. So friends, it's difficult to say whether we are using AI or ML or AI ML is using us. We should probably not get into that controversy whether our identity is at stake due to some of these applications, because that is finally our decision where we should allow AI to be used and where it should not be. So we should be completely aware of these facts before using AI into some domains. The applicability of data science in different fields has led to abundance of literature on utilizing sophisticated tools for handling big data, emergence of data science as an interdisciplinary engineering subject, and large-scale implementation of data science by industry, leading to the Industry 4.0, the fourth industrial revolution. The success of data science is not only about developing and utilizing mathematical algorithms and high computational power, It is also due to the domain knowledge as shown in the Venn diagram, which is considered as a very popular definition of data science. The intersection of machine learning algorithms, mathematics, statistical tools, and domain knowledge makes data science so much powerful. However, unfortunately, the conventional training in engineering is not in resonance with abundant advancements in data science. Therefore, to bridge the gap, there is a strong need for research works in process engineering aimed at weighing the pros and cons of data science from the point of a process engineer, providing novel solutions to the problems in database modeling, and exploring and realizing the potential of applying data science to process engineering problems. So as you have seen, there are two parts here: data science and engineering domain. Let's see the data science first. Data science can be defined as a combination of management, learning, and visualization of data. Here, learning resides at the core of data science, whereas the other two are related to pre and post processing of data. Learning can be broadly categorized as supervised, unsupervised, and reinforcement learning. So in supervised learning, the data given to you are labeled. For example, in any engineering process, you can collect the input-output data of the process, where you know if certain input is given to the process, what are their corresponding outputs. These are known as labeled data. You might try to build a data-based model to map the input-output relationship, or probably the functional relationship which can connect your input to output. So if this functional relationship is known to you, given an input, you can evaluate the output. Here, your outputs are continuous in nature. But this should not be the case always. In some cases, your outputs can be discrete as well. Say, for example, when you say that a set of input is only for producing a particular class of steel, and another set of inputs is for producing another class of steel. In this case, you target maybe to see the set of input and tell correctly which class of steel you are going to produce. In this case, you are targeting a classification problem. In unsupervised learning, the data are not labeled, and we are supposed to find the hidden pattern in them. Taking the same example of input-output data, what you can do is just hide the label tags of inputs and outputs from them, and then ask that given this whole data set, can we find out hidden patterns in them without knowing what is input and what is out? Of course, if you want to test your unsupervised algorithm's efficiency, you expect the algorithm will show relationship between several inputs and outputs without knowing their levels. That's the interesting part in unsupervised learning. Another example can be looking at the purchase records of several books. Can you cluster them into groups of most frequently bought books or least frequently bought books and books which are bought with medium frequency? This is the pattern analysis which Amazon does for you and give you recommendation after you purchase something from there. So this is something unsupervised learning. In reinforcement learning, the third one, you can imagine your machine as controller of the process. The beauty here is the machine is supposed to interact with the environment, that is your process, and learn how to control the process on its own. So what it does is it sends instruction to the process and receives reaction known as reward. So if the action is correct, you will receive more reward and vice versa. Over several course of such actions and rewards received, it enriches its experience and learns how to control the process. We have been working in almost all these aspects of machine learning. So various supervised learning tools can be artificial neural networks, support vector machines, decision trees, and we work quite heavily on artificial neural networks. The generic nature of ANNs, that is the short form of artificial neural network, is so fantastic that it can handle diversified types of data. Okay, for example, data can be static, which means data is not having any time component involved there. Data can be dynamic, that is time series data showing how a particular variable state is varying with time. For example, ECG data, stock market data. And third one, the data can be even an image. So that is learning from an image. The idea is, how do we learn from an image? The way we humans learn, can a computer or an algorithm learn from an image? After learning, can it draw a new image, etc.? All important aspects of computer vision. Though the names like AIML, ANN have been there over several decades, the popularity of the data science can be attributed to the relatively recently developed field called deep learning. The intersection of ANN and deep learning, that is deep neural network, is one of the backbones which enables automatic feature extraction of big data with the capability of handling various kinds of data sets, that is static, dynamic, and image data sets. So coming to the field of process engineering, most of the processes can be categorized into several unit operations, where operations are carried out from experimental scale to industrial scale. And these processes, irrespective of their scales, are governed by certain operating conditions that are going to determine the properties of the product. To find the desired properties, we tweak the operating conditions using optimization and control to run the process in optimal fashion. Most of these processes are very complex. If we want to capture actual behavior of these processes, we need to use highly complex mathematical models, which makes these models computationally expensive. This means these models take time to execute. For example, one simulation or function evaluation can take a day or even more. This is roughly the scenario we are talking about. So this is not at all uncommon. A computational fluid dynamics CFD model, which is used by mechanical or chemical engineers, can be a candidate of such type. With these computationally expensive models, real-time control and optimization of such processes is not going to be practically possible. This is because optimization is an iterative process which might call for such expensive function evaluation several thousand times. Each simulation taking 1 day time, you can imagine that the whole process is going to take several years. Hence, the plan is can we replace these time-expensive models with database models and perform optimization and control using them? Literature focuses various data science-based applications in this area, which are database modeling of the unit operations, surrogate optimization of the process, and control of such processes using database models. So on the other hand, with the establishment of computational methods, the field of process engineering is now strengthened with vast amount of proprietary databases and simulators. With this abundance of information in place, it is difficult to decide which one to use and which one not to. Suppose you have so many thermodynamic models in your hand to calculate equation of state in an Aspen kind of simulation environment, where sometimes there is no guideline on which model to use, or there are so many discretization schemes to try out in an ANSYS environment. So what are their impacts on your final outputs? That is, sensitivity or uncertainty analysis of such parameters on the outputs is another avenue where data science can play an important role. So in this way, we see the areas of process systems engineering, PSE, that is modeling, optimization, control, design, maintenance, and uncertainty analysis, where data science has shown a great influence. So with this background of influence of data science on applications around all possible domains, I am now going to cover some works done by our lab over the past several years. These will be primarily hovering with the applications of different forms of ANNs, artificial neural networks, and their applications in different areas of process systems engineering. So what are ANNs? Artificial neural network are mathematical representation of natural neural networks, which is composed of units called neurons, dendrites, nucleus, and action. Neuron is the fundamental unit of natural neural network. So if you see carefully, dendrites collect the information, modulate each signal, and transmit to nucleus. Nucleus receives all the signals and transforms it into single new signal. Action transmits the new signal to different consecutive neurons. Following similarity, scientists are successful to build a unit called node, which is the fundamental unit of ANN. In this node, the weighted input signals are analogous to dendrites. Information unit and nonlinear activation function do the job of nucleus. Activated output is transmitted to consecutive nodes, thus serving as action. So ANNs are collection of several such nodes. Now, based on the different types of connections of many such nodes, ANNs can be classified as feed-forward or multilayer perceptron neural network, where information going in the forward direction. Apart from this, there could be feedback or recurrent neural network, where a feedback loop enables simultaneous processing of current and past data, thereby handling a time series kind of dynamic data. Another kind of classification of ANNs based on the kind of data they handle is multi-layer perceptrons, MLPs. Okay, these MLPs are used to handle static data. RNNs are used to handle dynamic data, that is time series data. And CNNs, that is convolutional neural networks, are used to handle the image data. In case of static data, as shown in the figure, with K features and N data points, the sequence is not important, so you can shuffle them as you wish. But for dynamic data, the sequence is very important. We cannot change them. So now let's see how a neural network works a little bit in more details. Suppose there is a process with 3 inputs and 1 output. While building database model for such a process, we can replace the process with a neural network block with 3 inputs and 1 output, because the process is also having 3 inputs and 1 output. These are known as input and output layers respectively. In between these two layers, there can be several layers known as hidden layers, with each layer having several number of nodes, as I am showing on your screen. In the example given for you, there are 3 inputs, 2 hidden nodes, and 1 output, which can be expressed as 3-2-1. Data is given here as follows. For every 3 inputs, there is a labeled output Y. And we need to build a map between these inputs and outputs. As mentioned earlier, since this is a labeled data, this is a case of supervised learning. Now, what ANN does, it takes a particular row in the data set. That is 3 input values in the first row. We can process them through the neural network block to generate an output value represented as Y hat. So this processing is simple. So what we do here, weighted sum of all inputs are passed through the activation function placed inside a node. In this way, Y hat values are generated for every data point present in every row. Next, it calculates the mean square error for all these Y hats and Y. So Y is your ground truth value, whereas Y hat is your value of Y predicted by the neural network. The difference between these two, that is Y hat and Y, is the error. Okay, and this error is called as the loss function, which is minimized by manipulating the weights, all these weights and biases, and this leads to a closer prediction by a neural network to the data used to train it. So this process is called ANN training. The minimization of loss function with respect to weights is efficiently done in ANN using backpropagation. We can see the architecture over here. That is the number of layers, the number of nodes in a layer, the nature of activation function, different kinds of them like log sigmoidal, tan sigmoidal, ReLU, etc. are possible. These are known as hyperparameters of the neural networks, and they are decided a priori based on heuristics. So we'll discuss about this artificial neural network a little bit in more details. So as mentioned, this artificial neural network consists of input layer, hidden layers, and output layer. Now, based on your system, if you have 3 inputs to your process, then there would be 3 such input nodes in your input layer. If you have 1 output coming out your process which you are interested in, then there would be only 1 node at the output layer. And in between this input and output layer, there could be several hidden layers. Each one might be having several number of nodes. Okay. So input layer basically provides input to the neural network. And as I said, number of nodes in the input layer equals to number of inputs provided in the data. The information received from the input layer is processed by passing the weighted sum of inputs through an activation function. And this processing is done in the hidden layer. And all the nodes of the hidden layer will be connected to all the nodes to the next layer. The processed information is then further processed in the output layer. That is what the information moved to the next layer and is presented as network output. So you can see that in this picture. So suppose this is your input layer and you have several inputs. So all these inputs are weighted with certain weight. All these inputs are multiplied with certain weights and summed up in this unit. So you can see from all inputs, one or the other arrow is coming to this node, and above each of these arrow you can assume that there is a weight associated. Now every input is multiplied by this weight, and then sum of all these weighted input is performed in this block, and that output comes as y, okay, and that is fed to the activation function unit where it is activated, and the output comes out is known as x for the next layer. Okay, so in most of our slides further, this combination of summation unit as well as activation unit will be combinedly shown as by this blue color circular A unit. Okay, so though we are showing a 1 unit here, inside this there are 2 operations are happening. One is summation, another is activation. Okay, so you have several such layers in between input and output layer. They are all known as hidden layer, and then in each of these hidden layer there might be multiple number of nodes, and all these nodes are generally fully connected. Okay, and you can imagine what is happening inside each of this node. There is a summation operation as well as activation operation. Okay, so architecture of such a network is presented as number of nodes present in different layers. So first would be number of inputs. That is the first layer. Then the number of nodes in the hidden layer 1, number of nodes in the hidden layer 2, and so on, and number of nodes in the hidden layer n, and that would be followed by number of outputs. So you can see that probably a network which is presented above can be named as 2, 3, 2, 1, because there are 2 nodes in the input layer, 3 nodes in the first hidden layer, 2 nodes in the second hidden layer, and finally The layer shown to you is the output. So that means this nomenclature says the first number is the number of input in the ANN. Last number is the number of outputs from the ANN. And in between this first and last number, based on number of layers, you are going to say then how many nodes are there in each of these layers. So in between 2 and 1 here, there are two numbers, 3 and 2. That means there are two hidden layers. In the first hidden layer, there are 3 number of nodes. In the second hidden layer, there are 2 number of nodes. So you can quickly check and practice several networks with different architectures. These are quite self-explanatory. So in this case, we are expressing this network as 232. So you can understand there are 2 inputs and 2 outputs. In between input and output, there is only one hidden layer where there are 3 number of nodes. Similarly, you can call this architecture as 21321. Okay, so you remember one thing, that whenever we are presenting a node like this smartly, inside that there are two operations. One is summation operation, another is activation operation. So weights are generally the real value parameters which are multiplied to the inputs, and biases can be considered as weights whose input is unity. Okay, so here you can easily see through the cartoon that X is the input, which is multiplied by this weight W, and this is done with several other streams which are also coming as input, and they all get summed up along with another stream which is responsible for bias. So in case of bias, the input thing is assumed as an unity. So the B we are going to write is the weighted of this stream whose value is coming as unity. Now the product which comes out of this summation unit is known as Y. Okay, and when that passes through this activation function, that becomes X. Now I'll be talking a little bit about some notations of weights and biases because they are extremely important. So superscript, that is this, indicate the layer number, whereas the subscripts indicate the nodes. Okay, so for weights there are two subscripts indicating first the destination node and then the source node number. Okay, for bias only one subscript indicating the destination of the connection. In that way, if I write a convention for a weight like W weight superscript L and subscript ij, this means that this is a weight of Lth layer of the neural network. Superscript talks about the layer, okay, and subscript ij means that I is the ith node of Lth layer to which the information is passed, that is destination, and j is the jth node of L minus 1th layer from which the information is passed. So that is the source. So I is destination, j is source, and L is the layer number. So in that way, from this example, you can very easily understand that why this particular weight is called as Y superscript 1 subscript 1 1. Okay, so if you are getting a lot of ones here, you come to this way, which is weight of superscript 1 subscript 2 1. Because why subscript 2 1? Because this weight connects the node number 2, that is destination, with the node number 1, that is source, of two consecutive layers. But then this weight is connected with basically Lth layer. So that is what this is known as W superscript L. In case of bias, we are going to use one superscript, one subscript. Subscript is basically the ith node of lth layer to which the information is passed, whereas lth layer, L superscript is for lth layer of neural network. So in that way, you know that what would be the name of B11, B12, and B13. So this is a bias, you can say source of bias, which is connecting with first node, second node, third node, and in a way all possible node in the hidden layer. So you know that these weights and biases, they are used to evaluate the weighted sum. Okay, and after you evaluate that weighted sum, that is your y variable, which passes through the activation function, and after that it becomes another x for the next layer. So that is what summation and activation both happens inside this node. So whatever comes out of an activation unit, that is known as x superscript n subscript j. So this says that this is activated output of jth node in the nth layer. So if your output xnj and the input y1j, which is done just before entering to the activation unit, okay, so if they are same, then you can say that probably this is linear activation happening. Okay, so I will write down x, y, and all these things in this particular image so that it becomes easier for you. So you can see in an activation unit, x becomes your output, okay, and y becomes your input. You see in this node, x was your input. This stream is going to the next node for the next layer. There also x becomes your input. But then this x is different, this x is different, and they are presented differently also, because you have the superscript handle which tells that this particular variable belongs to which layer. Okay, so by that you will differentiate between this x and this x. Now what we are saying in case of linear activation function, when your x, which is coming out of your activation unit, when the y is given as an input, when they're same, then this is linear activation. Whereas in case of nonlinear activation, the same y goes inside the activation unit and passes through nonlinear activation function to give you a different value of xnj. Okay, so you just see here in case of linear activation, x and y were same. In case of nonlinear activation, x and y are not same. And this kind of linear activation happens at the output layer, whereas most of the other layer we use nonlinear activation. Okay, so activation functions imparts nonlinearity into the model. Okay, you will see the expression of activation function and you can easily understand why they are going to be nonlinear. Okay, the activation function chosen must be differentiable. This is another requirement. We'll come to know why they have to be differentiable. Some of the widely used activation functions are sigmoid or logistic activation function. You can see the dependence between your input and output. There is a sharp sign of nonlinearity. Okay, so in this sigmoid, log sigmoid function, you can see whatever positive input you provide to this function, it converts that into any number more than 0.5, but then with an upper ceiling of 1. Okay, so any number in a way you give to the sigmoid function, it maps between 0 and 1. Okay, negative number is less than 0.5, positive number greater than 0.5, but then it is in between 0 and 1. Similarly, there are tan hyperbolic function, which looks like such nonlinear. And here you can see everything is mapped in between 1 and -1. So in case of log sigmoid function, it was 0 and 1, whereas in case of tan sigmoid function, it is between -1 and 1. Okay, there is many such kind of activation function. One popular one is known as rectified linear unit or ReLU, okay, which looks like this. Basically, which says that anything positive, you get your x equals y, okay, and anything negative, the value is 0. Okay, so ReLU kind of function is found to be extremely useful for CNNs. Now, very briefly, let us see how training of ANNs are being done. So you provide all the inputs and it passes through the hidden layer and comes out as an output. And you know that we call them as y hat. Okay. Now, input values, you assume some values of weights and biases. Okay. When you know the values of weights and biases and given this input, you can easily simulate the predicted value of y, which is known as y hat. But then there is true value of y also available from the data, which is known as y. Okay, so difference between these two is basically the error, and you can assume several forms of such error. Okay, say for example, mean square error, mean absolute error, root mean square error. Okay, so that becomes your loss function. And when you see the loss is greater than certain tolerance, which is going to be in the beginning because your weights biases are not really properly tuned for any arbitrary value of weights and biases, you are not going to get a predicted value y hat closely matching with your true value y. So initially your loss is going to be pretty high. So since loss is greater than some tolerance tau, so this information is passed to the optimizer. What it does, it now changes the values of weights and biases based on the kind of loss value you have obtained. Okay, and your optimizer helps you to update your weight, which you assumed as certain randomly chosen value in the beginning. With these new values of weights and biases, you come back to the hidden layer and you predict your y hat again. So in that way, over several iterations or epoch, okay, you improve your y hat values, and your aim is to choose the values of such weights and biases which can takes your y hat prediction as close as possible to the true value of y. Okay, and when in this whole process, several iterations are needed, several epochs are needed. This terminology can be used simultaneously. And the moment you feel like your loss is less than tolerance, okay, so you basically come out and say that my training is done. Okay, so about this training, let us see. So these are the following 4 steps which are involved. One is forward propagation, loss calculation, gradient calculation, and weight update. Okay, so these steps A, B, C, D are repeated till a termination criteria is met. And as you can see, your data you can assume will be given in this form. Okay, each of these rows are your different data points. So if you concentrate and see, your first serial number is your first data point, where you have 3 input variables and 2 output variables. Okay. So in this way, if you see, this table represents 5 data points, 1, 2, 3, 4, 5. And each of the data point is having 3 inputs and 2 outputs. Okay, now very quickly we'll show you how a forward propagation happens in an artificial neural network setup. Okay, so suppose you have 3 inputs and they form your input layer, and you see exactly the way the animation is happening. That is what is being followed during forward propagation calculation. Okay, so you had 3 inputs you have seen. Okay, now each of these inputs is multiplied with a corresponding weight. So this W111 into X1, W112 into X2, W113 into X3, when all these things sum together along with B11, you get an output from this node which is known as Y11. And then this Y11 passes through the activation unit to give you X11. Exactly same way it happens for the next node. And these 2 nodes are present in the hidden layer. Now when such outputs X11 and X12, they have come out of the hidden layer, they became input for the output layer. So this input multiplied with another weight, this input multiplied with another weight, summed up here, and then that output is known as Y of node number 1, that is subscript, at the layer 2, that is superscript. So this Y21 is passed through another activation unit, which is known as X21, to finally give you Y hat. So you can easily imagine in the beginning, you don't have any idea about these weights and biases. You are going to assume random values for them. When you are going to assume random values for them, how can you imagine that your Y hat will be very close to the actual ground truth Y value? So probably it will be not, right? So you can see information passes through in this fashion to give you Y hat, and then each of this Y hat, that is what this ith I has been used as a subscript here. Each of this Y hat is compared with their corresponding Y real value, which is Y from your data set, because your data set comprises X and Y both. Okay, only you are taking help of X, predicting Y hat, and then you are matching this Y hat with Y. And this difference is error, you square them, and then you take the mean. So that is what this is, mean squared error. So this is error, this whole thing is squared, and then you are taking mean. So you see, you read it from right to left, mean square error. So first you evaluate error, then you square it, and then you take the mean of it. So that becomes your loss function, which is a function of your weights and biases. So that means if you change your weights and biases, your loss function is going to be changed. So what is your motto in ANN training? To come up with the help of your optimizer such values of weights and biases which gives you this loss function to the maximum extent of minimum value, so that your Y hat value goes as close as possible to the true Y value. So this can be, so training of ANN can be written as like this, argmin of this whole thing. Okay. In that way, very quickly you can see this forward propagation example. And so suppose we take the value of X1 and X2 like this, and its output value from the data set is this. Okay, and you have decided to use an architecture of 2-1-1. That means there will be two inputs, x1 and x2. There will be one output, y1. Okay, and there will be only one hidden layer with one node. So why I have taken this very simple example, so that the example becomes very clear to you. So to start with, you have chosen the weights and bias values randomly. Okay, now let's see what happens. So forward simulation, if you see, this is what is the calculation is. You multiply input with their corresponding weights. Same here, and then bias, add all of them. This y passes through the activation function, which has been chosen here as log sigmoidal value. This gives you this x11. X11 is nothing but the value of x at this point. Now this x11 would be multiplied with this weight and added with this bias, and then again pass through the activation function to give you the y hat value. Let's do and see. Every time I'm going to write these things so that there is no confusion in your mind. So x11 value multiplied with y211, okay, and then added with bias, that would give you y21. This y21 passes through the activation function to give the value of x21, which is nothing but your y hat here. Okay, so you got an y hat value of 0.5397, whereas the true value of y1 is 0.01. You are way apart. But no problem, you know the reason why you are way apart, because you have chosen the values of weights and biases quite arbitrarily. Okay, but then the target of ANN training is to choose or probably update your weights and bias values in such a manner so that finally after certain iteration, your y hat value goes as close as possible to y value. Okay, so this difference or error, say MSE, mean square error, is known as loss function. In many cases, people forget what is loss function, but then without loss function, it is very difficult. You will be at loss when we are doing ML. Okay, so you cannot afford to forget loss function. Being taught or being mentioned in this way also shows us that many people later on says that probably they know how ANN works, but then they feel like they don't know loss function. But then my warning to all of you is, without loss function, you will be at loss in ML. Okay, so you should remember what do we mean by loss function. So you understood how the forward propagation works. In many different ways you can define your loss function. They can be mean square error, they can be mean absolute error. Okay, and now so minimization of loss is done using gradient based optimization algorithm, for which gradients for the loss with respect to a particular parameter, that is weights and bias, needs to be calculated. So this is precisely the reason for which I mentioned earlier that why your loss function should be differentiable. Okay, and you will realize while evaluating this gradient of loss with respect to weights and biases, okay, you have to evaluate the gradient of your activation function also. So that is what we also mentioned, why your activation function should also be differentiated. Okay, so mentioning this, so what we have come up to, so we performed forward propagation, came from here all through, and finally obtained loss. Now basically your next goal is to update your weights. Okay, how these weights are updated. To update this weight, this expression is needed. That is what is the gradient of your loss with respect to this particular weight. I'll show you the final expression a little later. You will realize that this expression is needed there. So for the time being, I would request you remember that this expression would be required to update your weight. Now let us see, if you allow me, to proceed. And if I can say that you take my sentence as a matter of fact and allow me to continue, then I say that you remember for the time being that this derivative of loss with respect to weight would be required for you for updating your weight. Okay, so now assuming that is correct, let us see probably how to evaluate this derivative. Okay, so this derivative calculation would be a little bit theoretical, but believe me, this is pure chain rule of differential calculus, which is going to help you like anything. So I'll not go into many details, but I'll tell you at least how the whole thing happens. So you're interested in dou L, dou W, this particular term. So what we are going to do, we are going to use chain rule by taking the next variable into consideration. So you can probably remember your chain rule and you can be convinced that this can be written like this. So I just took help of this yi variable and wrote the chain rule like this. Now, anytime this loss with respect to any y is known as sensitivity. So that's what the first term is known as sensitivity. But you see dou y, dou w. Okay, so dou y and dou w, if you imagine, then you can think that that would be nothing but x m minus 1 j, because this x multiplied with this weight and then another input multiplied with corresponding weight, all added plus bias added will give you y. So when you take this differential of y with respect to this weight, you are going to get this input. Okay, so that is what this expression is. Now let us see what is this sensitivity. This sensitivity is nothing but dou L by dou y. That means dou L by dou y. I am going to use chain rule again by taking the very next available variable xmi. You see? Okay, so here also you can see that dou L dou xi, let us keep it for the time being. But then if you see dou x dou y, the term here, nothing but the derivative of this activation function. Okay, now let us see what is this dou L dou xi. So that means again, so can you see that you started with dou L dou W, from there you came to dou L dou Y, and then from there you came dou L dou X. So you are as if proceeding in this direction. So dou L dou Xi, here you can see the stream got divided into two parts. Let us see what happens with one part. And then if that is clear to us, then the similar term we can add for the other part, because here the stream gets divided into two parts. So dou L dou Xi is nothing but, let us take this part. I am going to take the help of the next variable and going to use the same chain rule. Okay, so if I can write this part, we can write this part also. That's what this summation sign is used, which is written in this compacted form. And then here I can again see I am experiencing dou L dou Y, which we always called as sensitivity. So this is nothing but, and you can see this term is nothing but the weight. Why it is like that? You can see this. Okay, so if you take dou of y with respect to dou of weight, you are going to get xi, and if you take dou of y with respect to dou x, you are going to get wi. So in that way, all these expressions, if you take or have a close look at your leisure time, they would be quite clear. Okay, so in that way, you came to know probably that how different weights in a neural network are updated. Okay, so or probably how you can evaluate the dou loss with respect to dou weight. So again, if we take the same example, then probably what we can see that we have with this set of input and output and architecture and initial weight, we did the forward propagation just few minutes back and we got this y. From here, from the data set, we know this is the target data. So we can evaluate the, you can say squared error, because this is about single data. So there is no sense of using mean, but then this is actually supposed to be a mean square error. Why? Because you have taken the only one data set, then you are going to do the second data set, you are going to do the third data set. So you're going to use all the data set in your training set. Okay, and then you evaluate their error square across all the data set and then take the mean. So that is what I have written MSE here, but then here the example we are showing only for one data set where mean doesn't mean anything. Okay, so it is all about one data set. I hope you understand that difference. So in the same way, the loss will be evaluated for all data points. And then, so when we see that, let us see probably what would be dou L dou W211. That is, what would be the derivative of the loss with respect to this weight? Okay, so this gives you this expression, which on further differentiation gives you this value. And so this is a summation of several loss terms, out of which one loss term we have evaluated here. Okay, because this here, the index I runs from 1 to n. So loss 1 plus loss 2 plus loss 3. So in that way, I'm just considering the first loss term. And let us see probably how can we evaluate this dou loss 1 with respect to dou W211. So, and we did this differentiation, which is pretty usual. Now we are seeing that now let us follow the conventions what we have stated in the class. Your y hat 1 is nothing but x21. Okay, x21 is the variable here, and which is coming out of activation function of y21, which is happening inside this, because you can see the combination of this y and x, and that y21 is a combination of this x11, w211 and plus b21. Okay, so if you do all corresponding differential operation, and you see I didn't do any deep math, I am just using chain rule. Dou y1 hat by dou this weight, I am going to replace this y1 hat by x21 because they are same. So these two terms are understood. And here I am going to take help of this additional variable inside y. Okay, inside this node there would be an y. Okay, and with the help of that you can see that your dou y1 hat by dou w211 is nothing but the derivative of activation function and x11. Now what is this derivative of activation function? If you do a simple math, it will show you that the derivative is nothing but the function into 1 minus that function. Okay, so in that way, f21 prime, which is appearing here, is nothing but your these input values. And in that way, you found that dou of y1 hat by dou of w211. Okay. So in a way, you can see that this complicated dou loss with respect to a particular weight, which is this weight in this case, is nothing but can be expressed very nicely with the help of an analytical expression. Similarly, you can write dou loss with respect to this weight, with respect to this weight, with respect to this bias, everything can be written. Okay. So something similar we did here with respect to, so dou loss with respect to this weight, dou loss, dou W211 we evaluated that, and then we evaluated that for bias also. You just remember for bias, this input value is 1. So wherever x1 is appearing, okay, so that value would be simplified. Okay. So similarly, we can evaluate dou loss with respect to dou W111. Okay, so I'm not going through this complicated expression. Since this weight will be far away from this loss, you see there will be more terms in the chain rule. That's it. Nothing more complicated than that. Okay, so in this way, you can evaluate probably for all weights and biases their corresponding derivatives. So dou loss with respect to certain weight, dou loss with respect to certain bias. In that way, you can evaluate all the dou loss with respect to weights and bias. And after all these calculations, probably you can see this is the equation which I told you that I'll be showing you later is known as weight update formula. So this weight update formula is going to be used where the old weight value along with the derivative of loss with respect to weight. This is known as say momentum parameter. Okay. And so you know your old weight value, you know this parameter, or you will assume this parameter, and we have just seen how to evaluate the dou loss with respect to dou weight, and you can get your new weight value. Similarly, you can get your new bias value. Okay, so in this way, you can evaluate probably several weights and bias values and tune your neural network more and more so that your predicted Y goes as close as possible to the Y data value or actual Y. Okay, so a little bit about training process we have covered in case of ANN, but here I'll just cover one more thing. So suppose there is a data set is given to you. So not the entire data set is going to be used for training. Part of it is used for training, say 70% of the data, and 30% is kept for two purposes, validation and testing. Okay, so 15% validation, 15% training. So you performed your training with 70% data. Okay, but then you don't show your validation and testing data to your training algorithm. So you only show your training algorithm only the training part of the data. So it gets trained with training part of data for certain number of iteration. Whatever weight bias values you got during training, you are going to use those weight bias values to now predict this validation data and calculate the error. Okay, so that is what at certain number of iteration, after certain number of iteration, you keep track of your this blue curve, which is basically the training error, and the yellow curve, which is nothing but your validation error. You see, you are not showing validation data to your training algorithm. It is just predicting. It is getting trained using the training algorithm, and then it is predicting the y-hat values for this validation data. Now, in both the cases, you can evaluate the error. You will see that after a certain point, your validation error will start increasing, whereas your training error will keep decreasing. So that is the point where we are supposed to stop the training, because what happens after that? So in the training part of the data, along with the trend of the data, there is always some noise present. So after this point, your training algorithm starts learning the noise present in the data, which we don't want. We want the actual trend in the data. So if we do not stop our algorithm at this point and allow our training algorithm to proceed more and more, then your data can be, or your training or your model can be overfitted with the data you use. So if you build a model which is overfitted with the data, then that model is not going to work that well with an unseen data. Okay, so that is what is a very specific feature in machine learning known as generalization, which makes it really different from curve fitting exercise. So this is precisely a very big difference between curve fitting and machine learning. Okay. So whatever we have seen so far, now based on that, probably you'll appreciate one thing, that these are the challenges in ANN. Design is based on heuristics, because how many nodes, how many layers, okay, or means they are all designed heuristically. There is no guidance for choosing the activation function. Which activation function to choose? I talked about so many of them. So there is no proposed sampling plan for placing the experiments in the data space. Okay, and these algorithms are data greedy. So now the question is, can we provide a remedy to such problem? So this area is currently a very hot topic in machine learning. Scientists from Microsoft Research and Carnegie Mellon University, two top organizations on their own merits, have joined hands through a project called Project Petri Dish to search optimal neural network architecture. And they started around 2019. This hyperparameter estimation belongs to a broad area of machine learning called AutoML. We are one of the first few workers who followed the evolutionary optimization route to address the problem of neural architectural search several years back. We named our tool as Transform, which stands for trade-off between accuracy, node, and sample size for meta modeling. This is a framework where, using a multi-objective optimization route, all hyperparameters are determined optimally. So what is needed as an input to transform, we named it as transform, is just the model of the process or the process itself. It can determine rest of the things shown on the right side of the figure on its own. So now I will talk about the broad idea involved in surrogate optimization. Since the unit operations involved in chemical, metallurgical, or mechanical processes are generally very complicated in nature, building the physics-based model needs consideration of a lot of physics involved in the process. This makes these models computationally very expensive. Performing optimization and control of such processes using such expensive computational models become almost impractical due to huge simulation time involved. So the question we try to answer here is, can we build a data-based surrogate model to these computationally expensive models? The advantage is such that, such data-based models are extremely fast in computation and thereby very apt for performing subsequent optimization and control. However, the challenge here is to closely mimic the high fidelity models. Here we are not talking about the error minimization between the prediction and actual data of the process. The model should be generic enough to predict a set of unseen data. So machine learning models should not be overfitted, as I mentioned earlier, and they should be parsimonious in nature, or they should be generic in nature. So as you can understand, there is a trade-off involved here. So more number of nodes bring in more number of parameters, which help in increasing the accuracy, but more number of nodes bring in danger of overfitting. So if we use more data, the model can be fitted better, but more data means more expensive experiments needed. Due to these two trade-offs, there is a third trade-off between sample size and total number of nodes. So our target is to attain maximum accuracy using less amount of data and less number of nodes to make the model most generic possible or parsimonious. We use multi-objective optimization route of minimizing the number of nodes, sample sizes, and maximization of accuracy. We use all the hyperparameters of the network to achieve the goal. Okay, so with this, probably now we'll move on to few applications. Okay, the first application we address here is surrogate-based optimization application using static process data. We take a polymerization process first, which is having 3 inputs and 4 outputs. One thing is very good about AI, that it is domain independent. I'm talking about polymerization process, but it can be any process. Say any mechanical process which can give you input versus output data. So in this case, inputs are monomer concentration, initiator concentration, and temperature, whereas the outputs are molecular weight, branching index, polydispersity index, and polymerization time. This is an experimentally validated model with 285 nonlinear stiff ordinary differential equations. Here we want to minimize polymerization time and maximize molecular weight and branching index to have a better quality polymer. Multi-objective optimization of this polymerization study takes around 15 days. Now the aim is how to make this optimization faster. So the plan is to build ANN-based surrogate model for this computationally expensive polymerization model and then perform the optimization with the time chip surrogate models. Of course, the challenge is to build a very accurate model. We used two types of ML tools here. One is ANN model and the other is Kriging model. Both are good capability wise. ANN, when used under our transform framework, could build a model with 280 expensive function evaluation, whereas the Kriging model used for 17 expensive function evaluation. So ANN model could build better accuracy surrogates with less number of expensive function evaluation. As transform also finds the optimal architecture, we can see the model architectures found by transform under the architecture column. 3511, this architecture means, as you know by now, 3 inputs and then there are 2 intermediate layers with 5 node in one and 1 node in another, and finally there will be 1 output. And we can see that T-poly model has a different architecture from M_W, this model. Okay, these architectures are different. We should remember that when no surrogate model is used, total number of function evaluations was 2800. So 2800 from there to 280. So we found ANN-based optimization as 10 times faster than conventional optimization. ANN is found to be nearly 1 time more faster compared to Kriging. So in another case study, we considered the continuous casting operation. Here we are trying to manipulate the 7 water spray flow rates and casting speed so that we can solve an optimization problem of maximizing exit temperature and casting speed and minimizing bulging simultaneously. Again, this is a multi-objective optimization problem. We use NSGA2, which is one of the very popular methods for solving multi-objective optimization problem. Okay. Again, the optimization takes a huge time as we use a 2-dimensional thermal model to solve the model equations. So can we make the optimization fast? So conventional optimization with time expensive physics based model used 2500 expensive simulations, whereas transform, which is our tool, could provide results with only 390 expensive simulations. So there is a saving of 84% function evaluations. And as you could see, transform framework could find ANN models with different architectures and transfer functions for different outputs. So now we use data science to analyze the optimization results. So we have 8 inputs, that is 7 water spray values and casting speed. We normalize them between 0 to 1 to have a common scale among all of them. Remember, any value between 0 and 1 is allowed for these variables. Now we take Pareto optimal points obtained after multi-objective optimization and perform clustering among them. This reveals 5 sets of operating rules given in slide by 5 different rows. Look at the first and last row. First row says if you want to achieve very high casting speed, relatively higher exit temperature and moderate bulging, you need to keep your spray values at certain ranges. These ranges are significantly different from the last row, where you want to achieve lower casting speed, relatively lower exit temperature, and similar level of bulging. These observations, if validated with the plant operations, can be used as operator's rule to run the plant optimally. And we know if an operator has to learn these rules from the scratch, it takes a lot of shop floor time. But what we could see here is a discovery of such operator's rule became possible as a result of AI and optimization based study. So that's great and cool, right? So the 2 case studies from iron and steel making industries show us that how machine learning can help us in augmenting our capabilities by performing optimization with computationally expensive models, which was otherwise seamlessly impossible or extremely time consuming. So now I'll take you through the journey of an ML algorithm through a video. So let's take a very complicated function which is having multiple number of peaks. Let's see if a ML algorithm can mimic it or not. So this is known as ACLE function. So you can see here how complicated function is this because it is having a lot of local minima. So the true function is shown at the extreme left. The middle column shows how transform is helping ANN to evolve towards closely mimicking the actual function. The last column shows the match between the predicted and actual output. When the predicted output matches the actual output, the point should lie close to the positive slope 45-degree straight line. So on your left, you see the true ACLE function, and in the middle, it is simulated ACLE function. See how difficult it is to find out which one is true and which one is simulated. Okay, so the now second topic is nonlinear system identification from dynamic process data for control applications. Now think of an industrial grinding circuit with 2-stage classification. This has 3 inputs, that is raw material solid flow rate and 2 water flow rates, one at primary and one at the secondary sump. The circuit output is collected at the secondary cyclone. Now performance of the circuit is observed by 6 output variables, which are throughput, 3 size classes, percent solids, and recirculation rate. We have an industrially validated model at our disposal for such a grinding circuit having these 3 inputs and 6 outputs. Now 2000 data were generated running the dynamic model. That means we are talking about time series data for the purpose of this system identification. It creates a time series data for us from which we need to model the dynamic behavior of the process. So which, as you know, is known as system identification. So what we did, 70% of that is first 1400 data were used for training, whereas 30% next 600 data were used for validation. So here you remember this is a sequential data, time series data, so we should not play with their sequence. So we need to maintain the sequence. Here we'll be dealing with another fundamental unit of neural network to handle dynamic data or time series data, which is known as recurrent neural network. You have seen that we have several multi-layer perceptron earlier for handling the static data. Feedback loop when added with multi-layer perceptron gives us RNNs. However, 2 problems in RNNs are it cannot handle problems of vanishing gradients and long-term dependency in data. So this comes another network known as LSTM, long short-term memory networks, to handle the time series data in much better fashion. Without going into much details of RNN and LSTM, I mentioned that depending on cases, we use both these kind of ANNs in our research or for time series modeling. So first, three pseudo-random binary signals, that is PRBS signals, are generated with for 3 inputs and corresponding 6 outputs responses are collected. These data is used to train the LSTM network. Next, a fresh unseen RGS, that is random Gaussian signals, are generated for 3 inputs to test whether the trained network using some other signals can predict the outputs for an unseen signal correctly or not. So these are the outputs of PRBS signals showing training happened quite nicely with the R2 or R square value of 0.99. We solved the problem using transform framework, which gave us optimal architecture of LSTMs. Okay. And when testing on a completely unseen data, the results show 98% match as shown here. We could see, or we could even show that using this kind of models, the grinding circuit can be controlled. So summary of this part is system identification for a complicated nonlinear industrial grinding circuit using LSTMs is successfully done. Analyzing the time series data, presence of long-term dependency is realized. Due to this reason, LSTMs are utilized to perform system identification. Using transform kind of framework, best architecture of LSTMs is also found out. The third topic is learning from image data to have the capability to draw the new images. So these images can be sourced while seeing, say, microstructures under the microscopes or any other relevant processes where images can be used to judge the performance of the process, whether the process is going correctly or not. As these decisions are quite subjective and can vary from operator to operator, researchers have shown that a machine-based decision making can do a very satisfactory or consistent job here. So here I'm going to talk about an image-based project we have done recently while targeting wind characteristics modeling. Since the wind characteristics is very stochastic in nature, when we calculate power in a wind farm, it is the average power that a group of turbines generates. Okay, suppose a turbine is standing at a location when it can face wind coming from all 360 degrees at different wind velocities. Wind frequency maps are the probability mass function curves drawn based on wind flow data available at a particular place. Based on the frequency of wind flowing at different speeds from different locations, these probability mass function curves can be drawn. So speeds and directions can be divided into several beans, and based on the wind flow for a particular means direction and speed, the probability of wind occurrence is expressed in terms of a fractional number for each of these beans. So the total power is the average power contributed by all these wind speed direction combinations multiplied by the turbine power curve. So the takeaway message here is any control optimization study in wind energy conversion system heavily depends on wind frequency map. So the wind frequency map represents the behavior of wind flow in an area. You can consider this as one scenario representation. However, analyzing real-time wind data, we know the flow of wind nature changes over time. So if we cannot capture variations in all such wind states, or if we do not consider all such scenarios to capture wind variations during design and control of wind farms, energy extraction will not be consistent. You will design a wind farm assuming a particular wind state condition, and it will not be operational when it faces other wind condition. And this is very practical. As you see, most of the turbines in a wind farm are not operating and standing idle when you pass by them. This could be one of the reasons. Through this work, we tried to capture various wind scenarios in a wind farm through real-time data and let the machine learning algorithms learn through them and then draw some new meaningful wind frequency maps based on learning. So for this purpose, we used CNNs or CAE, I would say, convolutional autoencoder. And the type of neural network used here is convolutional neural networks, that is CNNs. So CNNs help us to extract feature from images and store the important features in a compressed form called latent vectors. So what we did, we used 4 years of wind data from a real wind site and identified different wind conditions. Corresponding to these wind conditions, different wind frequency maps are generated. We convert them into grayscale maps. Once the grayscale maps are generated, important features of these maps are captured by the convolution layer. After passing this information through the multi-layer perceptron, we use the replica of the convolution operation called deconvolution to get the image back. The difference between the original and the image after deconvolution is used as a loss function, and the network is trained using the weights used in CNNs. Once the training of such a network is done, we get the latent vector, which has the information of features hidden in the image. But then image size might be very big, but the size of this latent vectors is going to be very small. So you can imagine this is a compression mechanism by which you capture the important features in the images. And this is what is shown here, that left-hand side shows the images used during the training, and the right-hand side shows the new unseen testing images that the trained network would draw. Okay, so you would hardly find any difference in most of these images. Okay, so summary of this work is limited amount of wind characteristic data was available for constructing wind frequency maps. This leads to inefficiencies in studies like wind farm layout optimization and control. A possible solution proposed in the ability of deep neural networks to implement generative modeling on wind frequency map. Up to 13 layers in convolutional autoencoder were explored. The best architecture could capture the features from the images very well. It can sound root mean square error to the tune of 0.01. And obtained latent vectors can be used to generate new images of wind frequency maps. Okay, so I think we have some time left. So in that way, probably we can use this time to go for another case study. Okay, so this is the fourth case study, is model-based uncertainty quantification in processed system engineering. To elucidate this concept, I take an example of uncertainty analysis in CFD model for supersonic flow over missile body. The expression given in the slide shows how the coefficient of drag is related with drag force, fluid density, speed of missile, and area. However, when you try to solve this problem using CFD model, there are many other parameters which determine the calculation of coefficient of drag, for example, order of discretization, flux type, type of turbulence model, etc. Now, these parameters bring in the uncertainty in the calculation of coefficient of drag. So through this work, we want to see which input or a group of inputs is most important to impact the output in a quantified manner. In machine learning literature, this problem is addressed using a technique called global sensitivity analysis. This is different from principal component analysis, where out of given set of inputs, a few most important ones are identified and their effects on the outputs are shown by ranking them in the order of affecting the output. In GSA, all inputs are considered and their effect on the final output is determined using Sobol index. Sobol index value lies between 0 and 1. 0 signifies no significance and 1 signifies most significant. And any value in between 0 and 1 quantifies the degree of uncertainty. But here the trouble is Sobol indices are expressed in terms of square integrals, which are difficult to derive and solve using CFD model equation expressions. So what we did in our work, we first built a novel product unit neural network based surrogate model of the original CFD model, and then derived the closed form expressions of those square integrals using PUNN model. So this enables us to quantify the effect of all uncertain parameters on the output. So to achieve this, ANSYS CFD software was used to generate 100 high fidelity simulations, which are computationally extremely expensive. Transform based PUNN optimization runs led to different neural network architectures for different outputs. For example, the optimized architecture found for the first output uses 3 inputs, 2 hidden layers, 2 hidden nodes, and 1 output as the architecture. For the second input, 6 hidden nodes are found as optimal. So here are the result. First 3 rows in the table shows the effect of individual parameters on the outputs. Next 3 rows show their combined effect, and the last row shows the effect of all 3 parameters. The same information has been presented on the right using a heat map. From here you can see that coefficient of rolling moment is most affected by turbulence model you choose during CFD simulations. Coefficient of lift is most affected by the order of discretization you choose during CFD simulation, whereas coefficient of drag is most affected by the interaction parameters than the individual parameters. So these are some observations we matched with the existing body of knowledge, but this is for the first time we could quantify their degree of uncertainty. So summary of this presentation is that global sensitivity analysis enabled us to derive closed form expressions for Sobol indices, which are indicators for sensitivity for any input. Optimal design of means such network, neural network is obtained by transform. Applying this concept on a practical problem of supersonic flow over a tactical missile using CFD model, sensitivity of several uncertain parameters are quantified for the first time. So what we could achieve through our works, look at the green 3-dimensional bar for each of the application. If you see the first 4 bars, they are the applications of MLPs. It indicates the multiples by which the speed of the optimization program got improved. It is almost 6 to 12 times speed improvement. For LSTM, CNN, PUNN, the next 3 bars, it is test set RMSE, that is error, with which the unseen data can be predicted, which you can find as very low. Okay, so I think we are reaching very close to our time. So for that interest, I'll skip some of the other applications. So this is our extended family whose hard work I presented before you. We welcome you all to Gokul. That is our lab. So one of our works on biofuel supply chain design for India is recently got media coverage. Okay, and several government agencies are interested in this work. This work is bestowed with the Best Paper Award in one of the international conference, and our work on lithium plus lithium-ion battery got cited in European Union roadmap document, that is Vision 2030, in the novel cell design section as the futuristic research using AI/ML. And these are some selected publications using machine learning in process systems engineering by Gokul members, which can be extremely helpful to many of you if you are interested. And hope you liked our ride with machine learning. Thanks so much for your patience, and I hope this lecture would ignite enough encouragement among each one of you to try machine learning as your future research.
Thank you,
I
Professor
request
Mitra.
Thank you.
So yeah, Kirish. So any participants have any queries, you can please ask.
And extremely sorry, since I didn't receive any message from any participants, so I continued. Okay, so
No problem, no problem. I think participant like your lecture, sir. It was really nice lecture. Yeah.
no, so actually
So there
from
is
my
one.
the intention is to cover as much as possible, because since
Yeah.
the whole thing is getting recorded, people can see these things at leisure later. So in that way, the whole aim is to cover as much as possible. And still you could see, probably due to paucity of time, we could not cover probably 2 of the applications, but it's all fine.
Yeah, but you have covered the wide topic in a short time. And
Yes,
not many things you already have mentioned. Yeah.
yes, at least static
So
data,
I think
dynamic data, image data, all, and then sensitivity analysis, all 4 things are covered.
Sir,
I think one
one question.
participant is having one question, please. Go
One
ahead.
participant
Yeah,
having
Girish.
one question. What is the difference between RNN and BPANN, sir?
Okay, so BPANN you are asking, right? That is backpropagation ANN. So we talked about ANN, we talked about backpropagation, we talked about the backpropagation theory. As you have seen, those dou loss, dou parameter means dou loss, dou weight, dou loss, dou bias. All those expressions which I was talking about, they are all about the backpropagation. Okay, so first of all, I'll tell you that we are talking here about 2 kinds of data. One is static data, means suppose there is a process going on, there are 3 inputs and 1 output. The process might be a batch process, but you are going to collect data at the end of the process. So there is no state variable changing with time kind of information available in that data. So it's a static data. What is your initial input and what is your final output? So if your data set is like this, then this is known as static data. And then there is another kind of data also we talked about, that is known as time series data or dynamic data. Okay, so where you are going to probably observe how a particular state variable is changing with time. Say any property of the process, suppose you are performing some changes in the process in a suppose it involves some liquid and you are heating it, okay, and due to change in temperature, its property is changing. So how that property is changing with time? So that is time series data. So if you try to model time series data, then the kind of neural network you use is known as RNN, recurrent neural network. Okay, and if you want to model a static process where this time series data information is not there, then you are going to use something called BPANN, backpropagation artificial neural network. So they are 2 different forms of ANN only, but used for the purpose of, one for static data modeling, another is called dynamic data modeling. So this is precisely the difference between these two. So I hope the question is answered. Yeah.
Sir, another question from the participant. If in case the large data set for a system is not, if in case the data related with the system is very less, then an NNN based control technique is powerful or modern control technique based is powerful.
Okay, so basically what you have observed that these are database techniques. Okay, so the data is food for such techniques. So if you do not provide food, so these techniques are not really very robust. Okay, so they need quite a large number of data, and to the extent of they are so greedy that as much as data you can give, probably these techniques are going to be extremely happy. Okay, so but having said that, you know that data generation is not so easy for any kind of process. In many cases, probably data generation will be extremely costly, but in many cases, data generation might be extremely cheap. So the cases where the data is abundantly available, in those cases, these database techniques are recommended. Okay, so now most of the cases you are going to use this data to for I would say for system identification, right? So basically the building the functional map between your input and output. So in case the data available is really less, in those cases probably these kind of models are not going to be reliable. But then there are techniques also. So I'll just talk about, suppose there are 3 inputs in a data set. Okay, so this can be compared in a 3-dimensional room you're sitting at. Okay, you have 3 inputs, you have 3 dimensions. So in the room you are sitting, if I tell you to represent this room and to represent this room, provide me enough number of samples. Okay, so what you can do, so your ideal should be that, okay, you can probably give me smaller number of data set, but they should be uniformly distributed in the input space, means in your room. So if you have less number of data, but then if they are most uniformly placed or sampled from the input space, then you can still identify the system as compared to the case where you have enough or same number of limited data, but not uniformly distributed in that input space. So I hope you understood that, right? So you can survive probably sometimes with less number of data also, but then that should be good enough or uniformly sampled from your input space. But then if you don't have a control that how can you conduct the experiments, then you are not really sure that even if you have less data, whether they are just from one corner of the room. So in that case, definitely your system identification is not going to happen in a good way. So what I'm trying to give you as a message, if you have less data, then definitely database techniques are not that good. We should go for conventional techniques. And if you have more data, of course, you should try the database techniques, but less data, more data, whatever be the case, your ideal should be the whatever space you are trying to capture or whatever input space you are trying to capture for your system identification, it should be uniformly sampled. So if uniformly sampled, you can still survive with less number of data and still come up with a good model.
Sir, another question.
Yes.
During training, if several local minima are appeared, then when to stop the training?
Okay, very good question. So first of all, I would say that what optimizer you are choosing. If you are choosing a local optimizer, then you will get stuck in the first local optimization itself. So you'll not be able to come out of that. Okay, but then if you're using a global optimizer, then this question is valid because
Another question, sir.
Yes.
How to decide this trade-off? Is there any rule related with?
Which trade-off?
That is related with the training of several local minima.
No, so I think that is not the trade-off. Probably the trade-off which is talked about here is basically the trade-off between training error and validation error. So that is what which I mentioned, that you have to keep track of this training error and validation error parallelly. So suppose you have decided that you will use 100 epochs or 100 iterations for training your model. So every 10 iteration, you keep a track of training error, validation error. Training error is used to change your weights and biases. Validation error is not used during training. You are getting some new set of weights and biases. You are going to those new set of weights and biases to predict the validation data. But that validation data prediction and actual data of the validation set is going to give you validation error. So every 10 iteration, suppose you keep a track of training error, validation error, training error, validation error. And I have already seen a plot where you will see validation error would be generally more than the training error, because you are using training data set to train your algorithm. So your model is getting trained with the training data set. But then it is seeing validation data as a new entity. So its prediction for validation data and error will be more. Okay, so validation error curve will be generally lying above the training error curve. You keep a track of that. At certain point in time, you will see training error curve is going down, whereas validation error, which was going down, suddenly started increasing. So by keeping this track, around that point, you are going to stop your training. So is that clear?
Yes, sir. Yes, sir. Shenge madam, having a question?
Yes, sir. I have a question. Regarding one case study. Can you hear me, sir?
Yes, yes, yes. Go ahead.
Actually, sir, I am working on one case study of a lithium-ion battery. As I saw that for the wind power generation, wind power, you have taken the images, and based on the images, you have withdrawn the data, and then convocation is done. So similarly, I am doing for lithium-ion battery, because there are number of accidents happening of that two bikes and all. So that project I am working on, but because it is a dynamic type of a study, every time we don't know what is happening internally to the lithium-ion battery. So will this method will work for it or no?
Yes, method will definitely work, but you have to collect data from different scenarios. As many as scenarios you can collect. Okay, so your model is going to be that robust. And so this is not an easy job though, because you have to let the battery go through different number of cycles, and at different points you have to basically break it and take the images if you are trying to take the image based route. Okay, so I hope you understood that as rich your data set would be, your model will be that accurate. Okay, to make your data set rich, you have to take images at different cycles, and you have to make your data set as rich as possible. Means larger number of data set would give you better accuracy. So of course the technique would work, but the thing is you have to enrich your data set by taking several samples at different point in time.
Actually, problem is data data sets problem is there. So we have put validation of the manufacturer data for the validation. Whatever manufacturer data of the battery is given, that is put as a validation. But when we take the actual condition, one to accident happened in nearby my places, so we take that data. So as you said that the training data and validation data, they are not mapping. Means there is something random values are coming. So that's why should I go with the first data, or should I go with the validation manufacturer data?
So if you go by validation manufacturer data, that would be, I think, probably not the accidental cases, right? Because most of the validation cases would be like the ideal cases. So
Yes,
there
sir. Yes, sir.
accident really doesn't happen. Accident
Yes.
happens after several cycles. Okay.
Yes, sir.
So if you go for that, you will not be able to capture the accident cases. You will capture probably what is the ideal condition.
Okay, sir. Yeah. I agree with sir. Okay. Okay. Thank you, sir. Thank you very much. Okay.
Yeah, thank you so much.
Hmm.